plus lunch sessions of National Seminar, Exploring Physics with Experts. In the second session, the first lecture is on Concepts in Optics by Professor Anurag Sharma. It is my privilege to introduce Professor Anurag Sharma. Professor Anurag Sharma is a J.C. Bose Fellow and Class of 66 Chairperson of Physics at IIT Delhi and has been teaching since 1980. His research has been concerned with propagation of light in imaging and waveguiding devices. He has published over 110 journal papers and over 200 conference papers. He is an outstanding academician, conferred with endless counts of awards and fellowships, including the very latest J.C. Bose Fellowship and highly prestigious Shanti Swarup Bhatnagar Award, Young Scientist Medal, S.K. Mitra Memorial Award, Anil Kumar Bose Memorial Award, UGC Meghnad Saha Award. He is a recipient of the Lifetime Achievement Award of IIT Delhi. He is a fellow of all the 3 Indian Science Academies, INSA, IAS, and NASI in India, the Indian National Academy of Engineers, and of OSA, the Optical Society, USA. He is currently the president of the Optical Society of India. It's an honor that we have Professor Anurag Sharma with us. Over to you, sir.
Okay, good afternoon to the participants, to everyone, to the organizers. And okay, you have stopped the...
Yes, sir. I have stopped sharing.
Okay.
Now you can please share your screen.
Okay, let me see. Can you see my screen?
Not yet, sir.
No, not okay. I have not yet shared actually. Sorry. Sharing. Where is the share? Oh, share screen. Okay. Yeah, can you see now?
Yes, sir. Okay. It is visible now.
Yeah, all right. Okay, so I'm going to speak on some concepts in optics. And when Pushpa asked me to give a lecture, so I started thinking how I should make a thread in this particular lecture. So what I have chosen is I am going to talk about the the concepts in optics which are purely theoretical, in the sense the ones which came out of the mind of this thinker. So what are the basic things that we have in optics? Of course, you start with rays when you talk about geometric optics. Then the waves were developed. Then the waves were identified as electromagnetic waves, and finally came the photons. And each of this, these happened at different times. Rays were known for, time immemorial, from Greek times and so on. Waves were first postulated in 1678, and EM waves in 1865, and photons in 1905. And what are the principles that I'm going to talk about? Fermat's principle, Huygens principle, which is Huygens-Fresnel principle, Maxwell's equations, and photon and the stimulated emission. So what is common in all these 4 topics that I have chosen? They are all products of the thought process, and they show the brilliance of the thinker. They have stood the test of time and are valid even today. Each one has been responsible for initiating a new era in the field of optics. So let's first look at, put this out of the way, sorry. I'm seeing some screen, just a minute. Okay, let it be. Okay, yeah. So Fermat's principle. I'm sure you have studied Fermat's principle in your college somewhere or the other. The original statement of Fermat's principle was the actual path between 2 points taken by a ray of light is the one which takes the least amount of time. What does it mean? It means if you have point A and point B, and the light has to travel from here, and there are several paths, this black line and this red dashed line and the blue dashed line, these are all nearby paths. That's very important. They are all nearby paths, possible path the light could have taken. then the light will take the one which is the smallest in time, which takes the least amount of time. So if I look at the same thing, let the time taken from A to B be TAB, and the time taken along the path 1 is minimum in this case, then that is the actual path. So if I really draw this time as a function of paths, I have written here path 1, path 2, path 3, but there can be some parameter which will decide these paths, and then that parameter will be in the x-axis. But here it is just notionally. So you see the time taken is minimum for path 1. So that is the actual path the light will take. It will not take this path or this path, because time is continuously decreasing if you go nearby paths. There's no minimum here, right? So what does it mean in terms of mathematics? That means the time taken, that means dt A to B is the total time taken from path A to B. Any variation in that must be 0. What does that mean? That means, whenever something is minimum, then a small variation will not make any change. We all know that the first derivative of function, if it is 0, then it is a minimum at that point, or a maximum. Will come to that. So this is the same statement. We have not written this del path by del some parameter. It is just the first order change in the path is 0. So what is dt? Dt is nothing but ds, where ds is the arc length, or let's say paths along the distance along the paths, divided by the velocity. And since the velocity of light is c by n, where n is the refractive index here, and it different along the paths, so that is why it is called nds. And if you integrate, if you substitute that here, then 1 upon c will come out, and that will vanish because of the 0 on that side. It means that the optical paths, which is called, this integral nds is the optical path. The optical path from A to B must be minimum. That is the Fermat's principle in the original form. So it is the optical path length is the shortest along the actual path. Later on, it was realized that this is not the complete statement, and hence the correct statement was that the actual path between 2 points taken by a ray of light is the one for which the optical path is stationary with respect to small variations in the paths, which is the same statement as this. This equal to 0 is not only for minimum, but also for maximum and also for stationary. What does it mean? If the paths are such that the path 1 is minimum, then that is the actual path, or it could be a maximum, then also that could be the actual path, or it is stationary. What does it mean? If there is a path, if you change on either side by a small variation, then there's no change. Then that path is also a valid path. So these are the 3 situations which occur in Fermat's principle. Path could be minimum, it could be a maximum, and it could be a stationary path. Stationary is like actually a point of inflection in mathematics. As we say, the curvature goes through a change. Here it is a one sign of curvature, here is another, and at this point it is actually changeover. So even the curvature is 0. Okay, so the minimum path is very common. In fact, in uniform space between 2 points A and B, the straight line is the shortest path. So that is why in uniform space or uniform medium, the light travels a straight line, which is well known. But what are the examples of other paths which are often not given so clearly in the books? So I thought I have created one example where all these will come together. So let's consider a reflecting ellipse. So this is an ellipse which is reflecting from inside. And let us consider A and B are the foci of the ellipse. This is focus 1, this is focus 2. And we know that in an ellipse, by definition, this length plus this length is always same, no matter where this point. All these lines are equal. So if there's a uniform medium inside this ellipse, then light ray from here, suppose there's a point source at A, the light will get reflected and reach B. Okay, and similarly, this will also reach B. And if I take a nearby path, we'll also have the same length. And that means each of this path is actually a stationary path, because nearby paths also have the same length. So if I want to plot, let us say I consider the definition of this point, but this angle theta. So at theta equal to 0 is this point, theta equal to positive values up to 90 are as you move here, and theta negative goes like this. So if I plot the optical path length from A to B after one single reflection as a function of theta, it will come out to be a straight line. What does it mean? That means if I take any point on this, it is a stationary point because nearby points also have the same value. So all of them are stationary. So all the rays from point A after reflection will reach point B because they have all the and this property we know in other context also, that if you have a point source here, the perfect image will be formed at B and so on. Now let us now construct an ellipse whose major axis is the same, but minor axis is now slightly larger. This red ellipse. Okay, we have sort of kind of inflated the ellipse here. Now what happens? Now this A and B are no longer foci of this red ellipse. They were the foci of this. So they are two arbitrary points which are symmetrically placed around the center. This is just an example. Now let us look at this yellow path which is going, that means A, P, and B. Okay, A, P, B is of course larger than A small p and b, and A small p and b is the original ellipse, so that is a particular path. So the A small p b or A small q b or A small s b, they're all equal. They're all equal. But in this case, since A and B are not foci of this red ellipse, they're not all equal. But you can see from here that this A capital P B is larger than A small p b. Similarly, A S B is larger than A small s b, and A Q capital Q B is also smaller, is larger than this. But as I move in this direction, this difference becomes smaller and smaller. So this path here, path going through P and small p, so the path is much difference is much larger than the difference here. And ultimately, when it comes to point P, that means the ray which is coming from A to R and getting reflected to go to B will have the same length as earlier. So what does it mean? It means that the path from here, if I now plot as a function of theta, the path will take, this thing. At 0 angle, which is at P, it is a maximum. Then it goes down. At Q, it passes through at this thing, and then comes to a R where it is minimum. And if I go down further, then it will again increase. On the other side also, it will start from P, go to S, go through S, go to T, which is again a minimum. Now, so what are the rays possible for this red ellipse now? The rays possible are P is a maximum, R and T are minimum. That means this ray is a valid ray. And this ray which goes to R and comes to B, and this ray which from A to T and comes to B, these are valid rays. All this S and Q rays are not valid because they are not going through a maximum or minimum. They are just going through a monotonic change here. Okay, so in this ellipse, you will find that this is an example of a maximum path because on either side the path decreases, and this is an example of a minimum path because on either side the path increases. If I take a point here, this particular path is larger than this, so on either side it increases. So this example actually gives you all the three cases together. With the black ellipse, you have the stationary condition. With the red ellipse, you have maximum and minimum condition. So that is a third example which I can give here. So Fermat's principle is consistent with Snell's law, which was established experimentally, and that is the success of the principle. Because principle, when you enunciate, there's no. This is just a principle that you have stated, but it sort of governs all the laws of all the cases which the Snell's law actually shows experimentally. In some cases, Fermat's principle gives results very easily. For example, the focusing in an elliptical mirror, as we just saw, or a parabolic mirror. It is very easy to show that a parallel ray of light from a parabolic mirror will focus to its focus. whereas doing it through a Snell's law would require more complicated algebra. It has led to the principle of least action in mechanics. Of course, Fermat's principle was the first one of this kind, and then it further led to other least action principles. And in mechanics, we have principle of least action. Okay, so the light propagation. Let's look at how far we have reached. The Fermat's principle gave the clue, or gives the clue about the path the light takes from one point to another. But how light propagates remains still a mystery. At that time, the corpuscular theory of light propagation, which was started by Descartes in 1637 and expounded by Newton to a great length in 1672, was in vogue. And Newton was a big man. It was difficult to oppose him also. So a lot of people actually believed in that particular theory of corpuscles. However, it could not explain many experimental results. For example, diffraction, it could not, and many other. But still, people sort of understood. In fact, I don't know whether you know that the famous Newton's ring were never observed by Newton. They were observed by Hooke experimentally. Newton only explained them on the basis of his corpuscular theory, and that was also wrongly. But somehow they are now known as Newton's rings. Okay, Newton's role is actually negative in those. So now, the next step in the how light propagates was given by Huygens. And Huygens' principle is again a purely theoretical thought by Huygens, and he proposed in 1678 the wave theory of light. It's not exactly a wave theory, but wave front theory, I would say, of light. And he introduced the concept of wave front and its propagation. And what he said, that if this is a wave front at a given particular time and position, then each point, and I've shown only a few points, but continuously every point on this wave front will act as a source of a spherical wave, which for this I have shown here, for this I have shown here, and so on, and a common tangent. And after a certain time, all of them will reach at a certain point by the velocity of light, and a common tangent to all these will represent the wavefront after that time. And this is what is, so these are known as secondary wavelets. This is the primary wave. This is known as the secondary wavelet. And from this wavelet, you can, of course, if this is a spherical point, this will be a spherical wavefront. But when you make a common tangent, then this will touch this wavefront at one point, and that is the common tangent that becomes. This was the Huygens hypothesis, and which became a principle after his success, because it was successfully, it could explain refraction, it could explain rectilinear propagation, and many other things. And so it became a principle, Huygens principle. One problem with Huygens hypothesis of secondary wavelets is that the being spherical waves from a point, the secondary wavelets being spherical waves from a point, will also propagate in the backward direction. If this is a point source, it will give you a full sphere. And so if you want to make a tangent here, there will be a tangent here, but you can also make a tangent on the other side. And hence, this will result in also a wave going backward, which was not really true. Wave is going only in a particular direction. Huygens ignored the backward waves without any justification. The principle could explain propagation of, as I said earlier, plane waves, spherical waves, refraction, refraction, and could not, however, explain diffraction. There was no, today, of course, we use Huygens principle to study diffraction, but actually, it is not really, Huygens did not could not explain diffraction on the basis of his principle. And that was done by Fresnel. Fresnel in 1888 used Huygens principle and the ideas of interference, which were already established by then by Thomas Young in 1803. So now you had the Huygens principle. You also had the concept of interference, basically concept of superposition. And he based his theory on these two things. What he proposed, that all these secondary waves which are coming from, what Huygens had done, he had taken one secondary wave at a time and taken a common tangent. What Fresnel said, that if I am trying to find the field at point P, the light disturbance at point P, then all these secondary wavelets, which are coming from all these points, will contribute to this, and they will all add in phase with their own phases. So this has traveled more than this, will have a different phase, and they will all go. And so they will all wave superpose, and they will interfere. That means they will add in superpose in along with their amplitude and phase, and to give the final amplitude here. So this was the theory given by Fresnel. Fresnel also extensively studied polarization and put forward the hypothesis of transverse nature of light. So the first time anybody who had said that the light is transverse was given by Fresnel. Okay, it's largely transverse. I mean, not exactly transverse always, but it can never be just longitudinal. That means if a wave is going in the z direction, you can have electric field in the z direction, but you'll have largely in the transverse direction. But you can never have an electromagnetic wave which has only Ez if it is propagated in z direction. That is largely the meaning of being transverse. In sound waves, you could have waves which were actually longitudinal, but not here. And that is so with that, he said that if you want to explain polarization, then you must assume the light will be transverse. So his understanding of these waves led him to introduce the obliquity factor, because in polarization it was known that if you change the angle, the effect of polarization would be different and so on. So he could see that there's an angular dependence of light luminance, and so he introduced obliquity factors. So what he said, at this point P, the field from a particular wavelet would be given by A, the amplitude of the primary wave, I by lambda, I'll just come to that, e to the power minus IKR by R is the spherical wave factor, and chi of theta, which is the obliquity factor. And chi of theta, what he gave was 1 by 2, 1 plus cos theta. So when theta is 0, this factor is 1. When theta is 180, this backward direction, this factor is 0. At 90 degrees, this factor is smaller, which is 1. This I by lambda was also introduced by him to satisfy the conditions of known results. And this also gave that the secondary wavelet scales in amplitude as 1 by lambda, and also has a phase difference with the primary wave, which is of pi by 2, because I is nothing but e to the power I pi by 2. So that means the light, which is kind of scattered light in some sense, is also out of phase with respect to this, in quadrature phase actually. Now, this provided a mechanism for suppression of backward waves, because then in this direction there was no wave. He introduced this factor, of course, ad hoc manner. Fresnel presented his theory for a prize to the Institut de France, which was the Academy of France at that time, in 1818. Poisson was one of the members of the jury. He objected to the theory as it predicted a bright spot at the center of a shadow behind an opaque disk. So if you have a disk here, which is opaque and is open on the other side, small disk, and you illuminate with, say, plane wave or a spherical wave, then what the theory predicted, that there'll be on the axis, just right behind the disk in the shadow region, there'll be a bright point. So other regions will be dark, but this will be a bright point. Now, this theory was very, very absurd. I mean, it looked very absurd that behind the shadow in the center, you have a particular bright point. And I have a picture here. You can see here, this is a picture which is experimentally taken by somebody. And this is the bright point you can see here. By arrow, I have tried to point out. I don't know whether you can see this clearly. This is what you can see. Okay. So this is the bright point. So he objected to theory that this is absurd, and hence this theory cannot be valid. Arago, who was another member of the jury, showed the existence of such a spot experimentally. The kind of experiment that I showed you the picture, he obtained this picture and showed that actually there is indeed a bright point behind the disk in the dark region, thus providing a proof of Fresnel's theory. And Fresnel was, of course, awarded the prize. This spot is known as the Poisson spot, who had objected to this, and sometimes Arago's spot, because he had measured, but not the Fresnel spot. Okay. That is the way things are. This is how. So Huygens-Fresnel principle. The Fresnel theory of diffraction has been highly successful. In fact, even today we are studying. Whenever we teach diffraction for Fresnel diffraction, we actually use Fresnel, Huygens-Fresnel diffraction theory. It explained most experimental results on diffraction and wave propagation. Even today, the diffraction theory we study in the class, as I said, is the same, even after, which was formulated 2 centuries back. The theory, including somewhat ad hoc obliquity factor, was rigorously, this is I here, rigorously obtained from other developed, later developed, sorry, it is spelling, later developed electromagnetic theory of light. We'll talk about that later. So Huygens-Fresnel principle established that the light is a wave. However, its nature still remained a mystery. What is oscillating in light was still a big question. Taking clue from water and sound waves, it was thought of waves in an all-pervasive media called ether. So there was an ether theory, which was actually started by Huygens only, and it ran for 300 or 400 years. It often provided contradictory results to its own predictions. Although ether theory was pursued for centuries, it was completely abandoned in early 20th century. So 1678 was when Huygens started his theory, and this is early 20th century, 1900 something. So about 300 years, ether theory reigned supreme. A lot of people believed in it, but actually it was a completely wrong thing. Then came Maxwell. In 1965, Maxwell put together, not 19, sorry, 1865. I must correct this. 1865. Just let me. Okay, sorry. Yeah. In 1865, Maxwell put together several known laws of electricity and magnetism, along with his modification of Ampere's law, to obtain a set of 4 equations for electric and magnetic fields. This was the first field unification. Before that, electricity and magnetism were treated as different fields, but then this was the first unification, and he obtained what is now known as electromagnetic field. Maxwell's equation that charge-free and current-free media can be written in this form. And then what he did, he combined these. From his equation, he obtained the wave equation in free space. This gave him the speed of wave, which was very close to the speed of light experimentally known at that time. Maxwell asserted, and this was just an assertion, and this is the brilliance of mind, as I said. He just asserted that this cannot be a mere coincidence, and it has suggested that the light must be an electromagnetic wave. In his book, which he wrote here, which I have shown here, in his book, he compared the speed of light experimentally measured with the one obtained from his equations, again, experimentally known values, and he made this assertion. So, I've just here a page from his book, and here, there are a number of things written here, but basically he says the velocity of light, which was directly measured by Fichot and Foucault and others, was these numbers. This is meters per second, and the ratio of electric units, because what he said that the velocity of this electromagnetic wave which he has obtained is the number of electrostatic units of electricity in one electromagnetic unit. So this is what 1 upon epsilon into mu square root that we understand today is. This is how it was enunciated at that time. So using those again experimentally measured quantities, he obtained the velocity of those waves, and the numbers were very close together, although you may say that there's a difference. But later on he writes, it is manifest that the velocity of light and the ratio of units are quantities of the same order of magnitude. Neither of them can be said to be determined as yet with such a degree of accuracy as to enable us to assert that one is greater or less than the other. It is to be hoped that by further experiment, the relation between magnitudes of these two quantities may be more accurately determined. And then he says, in the meantime, our theory, which asserts that the two quantities are equal and assigns a physical reason for this quantity, that means the velocity of light is same as velocity of those electromagnetic waves, is certainly not contradicted by the comparison of the results such as they are. So he was very modest in saying that they're not contradicted, but actually he was trying to assert that what he has proposed, that this electromagnetic wave, which comes from his equations, is actually nothing but light. No direct proof of light being electromagnetic wave was obtained before the death of Maxwell in 1879. The first direct proof was provided by Heinrich Hertz in 1885 when he produced electromagnetic radiation through a spark. Of course, that was not light; it was a megahertz radio waves, but nevertheless, the waves were produced. Kirchhoff, who was a teacher of Hertz actually, used Maxwell's equations to obtain a diffraction formula very rigorously from mathematics, which showed the validity of Fresnel's diffraction formula, including the obliquity factor. So the obliquity factor, which Fresnel had put in an ad hoc manner from his knowledge of polarization and other field factors, actually turned out to be mathematically correct factor. So the diffraction integral, which we studied today, is also called sometimes Huygens Fresnel Kirchhoff integral, because Huygens gave the original principle, Fresnel modified it, and Kirchhoff showed that it is really correct from the Maxwell's equations. Okay, so with Maxwell's contribution and Hertz experiment, the electromagnetic nature of light was firmly established by the end of 19th century. However, Hertz experiment also revealed a new phenomena, and this is what we always say, the experiment which is giving you a proof of something is also actually giving you its negation in some sense sometimes. So this is what happened in Hertz experiment also. There were new phenomena of photoelectric effect. It was not the first time that this kind of effect was observed. In different forms it was observed earlier, but this was a conclusive photoelectric effect that Hertz had obtained. Further experiment showed that the energy of the ejected electron depended on the frequency of photon rather than on the intensity of light beam. This was contrary to the Maxwellian picture of waves, in which more energy meant more intensity. More, we all know that the energy, the S factor, is E cross H. So more electric field, nothing to do with frequency in that. So this again opened a new question: what is light? Because if light is electromagnetic wave, then this photoelectric effect could not be explained. In 1901, Planck had hypothesized that the energy could be emitted only as discrete amounts to explain the blackbody radiation curve. However, light was still assumed to be waves. Photoelectric effect, however, was at loggerheads with the wave nature of light. A resolution of this problem required the genius of Einstein. The greatest genius that we've had is no doubt is Einstein. And Einstein was one person who was really a master of thought. Most of his papers, there are no experiments he has ever done. Most of the papers actually started from scratch and thought a new idea. He invented the concept of thought experiment, which is called Gedanken in German, thought experiment. So, he could think of the experiments and, how to do it, and then what the results expected and how to explain the results. During 1905, which is known as the Annus Mirabilis, that means Year of Miracles, he wrote 5 papers. We all know this probably, purely from his thought process. Each one founded a new area of research in physics, and each one could have got him a Nobel Prize independently. In one of these 1905 papers, he explained the observation made in the photoelectric experiments, making an assertion that light exists as discrete packets of energy, which are called quanta. Einstein wrote in his paper, when a light ray spreads out from a point source, the energy is not distributed continuously over an increasing volume, but consists of finite number of energy quanta that are localized in points in space and move without dividing and can only be absorbed or generated as a complete unit. This was the concept that he gave at this point. Many physicists, and this is interesting, this is 1905, many physicists, including Planck himself, Lorentz, von Laue, Wien, Sommerfeld, doubted Einstein's hypothesis on the basis of the fact that the interference of light exists and which requires the wave interpretation. This photon becomes more like a corpuscular theory, and corpuscular theory of Newton could not explain interference, and so so that was the knowledge at that point, and they all did not agree. They doubted that what Einstein is saying is actually correct. However, in 1916, Millikan's experiment validated Einstein's equation for photoelectric effect. But nevertheless, even he did not accept the hypothesis of light quanta. The physics community finally accepted the quanta of light after Compton effect in 1923. And it's only after that the term photon was coined in 1926 by Lewis, who was actually a physical chemist, in one of his papers. So till then, it was not, photon word was not there. Light matter interaction is the next thing. At that time, which is the time of 1905 to 1910 and so on, 1910 and so, the concept of energy transitions in atoms mediated by absorption and the emission of light, quanta, was not commonly accepted by physics community, the way Einstein was thinking. Bohr's theory of hydrogen atom did not utilize the idea of photon. In fact, Bohr rejected the concept until 1920s, early 1920s, basically the 1923, which is Compton effect time. In 1916 and 1917, in these 2 years, Einstein examined the emission and absorption of radiation by a collection of atoms or molecules. And in this process, he postulated the existence of a mechanism of emission. And this was also purely a thought process. So what happened? Emission of light and absorption had been observed, and in fact, explaining the emission of a blackbody radiation was responsible for the development of quantum theory. In his study, Einstein recognized 2 classes. So he separated the 2 classes of interaction. One is the spontaneous, the other is the induced. This is the word, he used the word induced. Of course, the paper was written in German, which later on we call as stimulated. The latter process required the presence of radiation. So now this is the spontaneous emission. That means you have an atom in the upper level and spontaneously comes down without any interaction with radiation. But then this is the regular absorption, which is you have a photon coming or a light coming, and it is absorbed and takes the atom from lower level to the higher level. What Einstein said, that when a photon can interact in this level, why can't it interact with an atom in the higher level? And this is what he says, that there should be symmetry or reversibility at the microscopic level. And hence, when a photon comes and you have an excited atom, then it will interact with it, it will come down, and consequence will be 2 photons. Einstein further argued that the 2 induced transitions, that means induced absorption and induced emission. In fact, induced emission was sometimes called negative absorption also, just to not to use the word emission to be confused with this. So Einstein further argued that the 2 induced transitions, that means induced in absorption and induced emission, should have the equal probabilities. Though in equilibrium, as the lower state is more populous, absorption would be more. Using these arguments, Einstein derived the radiation from a collection of atoms or molecules and obtained Planck's radiation formula. In this process, he obtained the relations for the coefficient of spontaneous and stimulated processes, which are now known as Einstein's A B coefficient. So he said, for this, there's a A coefficient. For these 2, it is a B. The 2 coefficient must be equal to the same argument that we have read earlier. Einstein also showed in this process itself that the light photons that interact with the collection of atoms or molecules, either through emission or absorption, must be of the frequency nu, such that the photon energy h nu is E2 minus E1. So it should exactly match, only then it will interact. And the light interacts with matter as photons of energy h nu. Finally, the photon that is emitted during the stimulated or induced emission is identical in frequency, phase, polarization, and direction as the incident photon. This is really a remarkable consequence and has been responsible for the coherence properties of laser beams. But for this, the lasers which are coming out will not be coherent. So although there were some confirmatory works earlier on the stimulated emission, the experimental proof came in 1954 when Towns and Shallow invented measure based on this particular phenomenon. Measure is a microwave amplification through stimulated emission of radiation. Subsequently, the first ruby laser was invented on May 16, 1960, as Professor Ghatak said in the morning. May 16 is why is called the Day of Light by Mayman. So what happens in a laser? So you have a collection of atoms in which one photon comes and there's a stimulated emission. So you have excited. So basically what is required if you want to dominate stimulated emission over induced absorption, the number of atoms in the upper level should be more than the lower one. That is known as the condition of population inversion. So for a laser, that is necessary. Otherwise, this photon will have more probability of getting absorbed than leading to a induced emission or stimulated emission. So, but let us say you have more atoms here. So this photon will create two photons. Then there are two mirrors on the side to make a cavity. So these two are reflected back, and then when they come through again, they become 4. Then they come back, they become 16, 8, and 16, and so on. And within no time, they become millions. And this mirror, one of the mirrors is kept as 100%. The other mirror is kept less than 100%. So the part of the beam comes out as a laser beam. That is the output you have. So usually the energy that inside the intensity of the beam that you have, which is coming out, is only a small fraction of the intensity that is inside the laser. It's because this is usually 95% or 99% or 98%. The cavity, as Professor Ghatak had mentioned, but we'll not go into the details. He also could not have time to go. Cavity also is responsible for making the line refined. In the sense, the monochromaticity of the laser beam is actually responsible, is due to the this particular cavity or resonator. So lasers have really revolutionized optics, and some of the examples were given by Professor Ghatak in the morning. In fact, in order to encompass the vast new areas developed and numerous applications, a new word photonics had to be coined in post-60s. Lasers are now ubiquitous in everyday life, from laser scanners to oximeters. I don't know, the oximeters that you have on your finger to fight or to monitor your COVID kind of things is actually a laser device. If you see inside, there's a laser. The 120 years of history, and Professor Ghatak also, talked about some Nobel Prizes in his talk, and I give you some statistics here. In the 120 years history of Nobel Prize, they started in 1901, and today we are 1921 to 2021, is neatly divided by the lasers in the middle at 1960. So you have pre-laser era, which is 60 years, and post-lasers, another 60 years. So the pre-laser era of 60 years, the full Nobel Prizes are given to optics. In the post-laser 60 years, 14 Nobel Prizes have been given to the optics and photonics. So you can see the jump after lasers. So lasers have really revolutionized thing, and this is all started with the thought process of one person called Einstein. The photonics industry is expected to grow at the 8% annually in the next 5 years. However, in our country, we are just waking up. Okay. Thank you very much. Wake up.
Sir, we are wide awake. Don't worry.
No, I'm talking about with respect to the optics.
The whole optics is revised, sir. The whole optics is revised. In such a easy
Thank
manner.
you so much. Thank you for such an excellent talk. You took us all on a journey of Fermat's principles, Snell's laws, and all theories of light, corpuscular, then wave theory, and then Maxwell, basically electromagnetic theory, and also a bit of wave particle duality. And you also made us understand the concept of lasers once again so beautifully. So thank you so much. It was really very, very good. And let me see if there are any questions on the chat box.
No, ma'am, no questions are there.
Oh, everything was so crystal clear. So,
Yes, ma'am.
Yes, it was
That's
so
a
well
standard thing.
explained, sir. It was so nice.
yes, sir, very nice. Indeed, an excellent talk, and we are really
Yes, sir.
thankful. Therefore, you specially
When there's
prepared
no
this.
response, when there's no response from the system, either the system is totally transparent or it's totally reflecting. Okay.
No,
It
no,
was,
sir.
it was
Absorbed,
not
everything
transparent,
absorbed.
sir. It was absorbing everything, so nothing will come out. So
Sir,
if it is
Yes, sir.
absorbed completely, nothing will come out, sir.
Yeah.
And the best part is that, sir, most of the time the BSc students, when they are questioned in any particular interview or in any examination, I find that this part of Fermat's principle and Huygens principle is just not clear. Any question on Huygens principle, I've never seen any student answer amicably or appropriately, because there lies a certain amount of confusion in the mind. And with just one small paragraph there in NCRT, so by class 12, they are not at all clear over it. And in the graduation optics syllabus, though this is basics, but because it is descriptive, they just look at the diagram and move ahead and do not really understand. So your lecture gives them a wonderful opportunity to think about it and how it is all linked. And people also don't, students are also not able to link this and Maxwell's equations together. So that part has come out so beautifully, sir. It was very nice. Thank you so much.
Sir, somebody
In
has
fact,
asked.
in school books, I don't know where. I mean, I've tried to find out this several times, but in many books, what is, when you talk about diffraction, they will say bending of light at
Yes,
at
yes.
edges.
So
And
here,
I have been telling the students that nothing could be more wrong.
yes, exactly, sir. In
And
fact,
when I start teaching the first year, second year students optics, I say the first you forget. When I ask what is diffraction, they will all answer the same thing, more or less. I say you first forget this. Let me erase this, and then I'll write something else on it.
very true, sir. Sir, here I would like to just mention to you that when I started doing a teacher training workshop with Nasi Delhi chapter, then I asked the teachers, what would you like to clarify on? What would you like to understand as a teacher from an expert? And the first thing was polarization and diffraction. I was very surprised that teachers are very, very experienced, but they said, no, this is the point of confusion, diffraction and polarization. And then Professor Ghatak had explained the whole thing to them in that particular series. So it is a point which leads to some confusion in many minds.
Another thing which I don't know whether you are experienced, but I have sometimes gone to school teachers, lectures, some DPS or KV, etc. They call me sometimes. One thing they do not understand is total interreflection.
Oh, no.
The concept of evanescent wave is just not there. They think that everything comes back, everything is reflected. Total reflection means nothing goes on. There's nothing on the other side.
Yes.
It is, and I say that you have all done BSc, MSc. I mean,
No, sir, evanescent wave, I don't think is explained much.
No, it's not. Ma'am is
It's
correct.
not.
Evanescent
Yeah,
wave
it
is
is
not
not.
explained.
No, it is not explained. We did that in research, not in BSc or MSc.
So even in MSc, many students don't understand this evanescent wave concept and take total internal reflection to be really total in the true sense of the word.
So we need to do research for that, or to listen
Sir,
Professor Raj Sharma's lecture for that.
Sir, somebody has asked a question. May I read it?
yeah, please.
Yeah, somebody has asked, sir, is it like most of them are found out of some analogies, like Maxwell's equation and all? Basically, I don't know, the question is not very clear. Maybe the student wants to ask that these theories are developed out of some analogies, that means some thinking, like
No,
Maxwell's
of course,
equation.
no. You see, what I have tried to say here is that all the principles and theories that I talked about are not based, not a follow up of an experiment or explaining an experimental result. They have come from the thought process. Of course, when somebody thinks, it's not that anybody on the road can think of this. I mean, you can think of useful or meaningful things only if your mind is prepared, and that means you already know what is going on, what the experimental values, experimental results are, and so on. You know what is going on. Only then you can actually give a thought process and give you a new principle. I mean, it is not just like that. I mean, it is said that Einstein has given many papers. His papers normally have very few references also. But it's not that, he did not know of the literature. Of course, he must have known the literature, but few things probably he thought of, but he thought very differently. Very
So
differently.
Gatak sir always says, where did his papers come out of his mind?
Yeah. No, that he says for the Schrodinger equation.
No, for all these papers, 5 papers that you
Yeah.
talked about.
In fact, yeah, of course, all of them. But there were few things which were done earlier. I mean, I'm sure he was aware of those, so on. But that is, I mean, for example, the speed of light being constant. He was not the first person to think of that. There were others, but others did not have probably the courage to say that, because it was a very radical idea. So
Yeah. Sir, that graph
happens
of,
sometimes.
sir, that plot of part difference versus theta was too good. Very good.
Yeah.
Yeah. Actually,
Okay.
never thought like that.
Yeah.
Yeah. So thank you so much, sir.
Okay.
It was a very, very interesting talk. And once again, you spared so much of time for this talk. And thank you. We are really indebted. Thank you
Okay,
so
my
much.
pleasure.
Yeah.
Yeah.
I
All
think
right.
Professor, yeah. So I think
Professor Vijay Singh
Professor,
is